Hello, my name is Forbes Walker. I am the Environmental Soil Specialist for the University of Tennessee Extension. And today I'm going to be talking about Tennessee's nutrient reduction strategy. So let's start off by why do we need a nutrient reduction strategy? As many of you are aware, I'm sure there are many nutrient-related water quality issues around the country. Some great examples come from the Everglades in Florida a few years ago. We've had cases in Iowa where people have been suing agriculture and fertilizer application because of impaired waters there. Lake Erie for a number of years has had algal blooms, which has impacted the water intakes for the city of Toledo. The issues around the Chesapeake Bay are well known, as is the Gulf of Mexico hypoxic or dead zone, which occurs most years. The EPA is also asking states, and have been asking states for a number of years, to develop numeric water quality standards for nutrients, primarily for nitrogen and phosphorus. The idea being that they will set a limit and say this is the maximum concentration of this particular level of phosphorus we want in this waterway. If we see any numbers above, there's obviously some problems. These are two maps on the side here, one showing the total phosphorus and the bottom one showing the total nitrogen, come from the United States Geological Survey. It's no surprise that a lot of the total phosphorus that we see in the Mississippi River Basin is coming from the Corn Belt, where most of the grain crops are grown, similarly with the nitrogen. So these are some of the concerns that people have. So how did the EPA have the authority to regulate this? It comes from the Clean Water Act of 1972, which basically gave the EPA the authority to implement pollution control programs. They were asked in this act to set water quality standards for all contaminants of surface waters, and made it unlawful to discharge any pollutants from a point source, usually from a pipe, an industrial source, into the navigable waters without a permit. As part of the Clean Water Act, they implemented a permit process known as the NPDES, the National Pollutant Discharge Elimination System permit. These are the types of permits that wastewater treatment plants have. And in these permits, the EPA will say, you cannot discharge more than this amount of nitrogen or more than this amount of phosphorus. And phosphorus and nitrogen are the two elements that they primarily looking at. These are very important both for plant growth and crop growth, two very important primary nutrients, but they're also very important for algal growth. If we get nitrogen and phosphorus into the streams and rivers, it'll still stimulate algal growth and ultimately leading to impairments in the water. As of 2020, you can see on this map here, some states have implemented some fairly significant levels, especially Hawaii, of regulations on criteria for nitrogen and phosphorus, whereas other states, Florida, the upper, Wisconsin and Minnesota, have limits on either nitrogen or phosphorus. And many states, including ourselves, we haven't got any numeric water quality criteria. And we'll discuss, some of the reasons about that. As we mentioned, the authority to regulate these nutrients comes from the 1970s, from the Clean Water Act. The acting administrator of the in EPA, Nancy Stoner, back in March of 2011, produced a memo, and these are things that these administrators do at periodic things, basically stating that still 50% of the streams had medium to high nitrogen and phosphorus. Nitrate violations had doubled in the last 8 years. Nitrate levels were exceeding background levels in most of the monitoring wells. However, rather than demand once again that states set numeric water quality criteria, she did say in this particular memo that states need room to innovate and to respond to local water quality needs. So what happened then? So this was back in 2011. So the EPA, I'm going to talk about 3 case studies. One of them is Florida. This is where the EPA basically looked at Florida and decided to make an example of them. And Florida weren't making any actions, so they forced them to take some actions. And we'll see what happened in the Florida case. Then we'll talk about some of the more proactive cases, case where Mississippi developed a strategy, which is something which we in Tennessee very much mimicked their strategy. So what happened in Florida? So back in 2009, the EPA once again determined that numeric nutrient standards were needed for Florida. This is, set a limit for the amount of nitrogen, the amount of phosphorus in their waters. 2009 in August, the EPA entered a consent decree, which was revised subsequently in June and October 2010. The proposed criteria were proposed in January of 2010, and then in November 2011 they were finalized. And this is what Florida came up with. You can see the limits they have for nitrogen in this middle column here, and the ones they have for phosphorus in their streams and rivers. You can see there's different criteria depending on which part of the state is. That is basically because what we're doing is one number is not going to fit everything across the whole state, given differences in geology, differences in soils, differences in climate, and differences in in vegetation. One thing to note from these particular things is how low these numbers for nitrogen and phosphorus are. Very, very low numbers. The challenge we have here is how can we meet such standards? Also mentioned that if we had to throw up a map of Tennessee, we do have the middle part of our state, especially around the Nashville area, we have a very rich phosphorus geology. So the rocks there are naturally very high in phosphorus. So it's going to be very difficult to come up with some agreement as to what kind of levels we should be setting here in Tennessee. This is a set of numbers that they developed for their lakes and for the chlorophyll A in some of those lakes. Again, lots and lots of discussions, lots and lots of scientific debate as to what numbers should be set. And the challenges then become is how do we actually implement some of these rules? So that's what happened with Florida, who basically didn't take a stance and let EPA tell them what to do. Mississippi, on the other hand, took a more proactive approach. Back in December of 2009, they developed a nutrient reduction strategy working with Delta Farms, so farmers and a farmers group, Farmers Advocating Research Management, and the Mississippi Department of Environment and Mental Quality. And some of the things they mentioned in this particular strategy was what kind of load reductions are possible, how much is it going to cost, what is the value to the stakeholders, and will this actually lead to any changes in the waters of the Gulf of Mexico. So this is something that Mississippi did back in December of 2009, and we in Tennessee looked at what Mississippi had done, looked at what was going on in Florida, and decided to let's follow the route that Mississippi is going and start to develop our own strategy. So we started work on this back in April of 2010. It was a collaboration between ourselves at UT Extension, as well as officials at Tennessee Department of Environment and Conservation in Nashville, as well as officials at the Tennessee Department of Agriculture. We basically worked for a little over a year amongst ourselves, developed a draft document, which we then presented at a meeting held in Jackson, West Tennessee, December 2011. At this meeting, we had a number of people there. We asked them for some feedback. We got lots of very valuable feedback, which we then used to modify the document. We presented this document at a meeting of the Gulf of Mexico Watershed Nutrient Task Force in April of 2012. Should also note that we actually were a year ahead of Kentucky and Iowa and other folks in the Mississippi River Basin. I'm not going to bore you with the details, the nitty-gritty of this particular document, but this document is now available on the EPA Mississippi River Gulf of Mexico hypoxia website. All the states within the Mississippi River have a nutrient reduction strategy. And if you click on Tennessee's one, you'll come to a site here at the Department of Ag, which will lead you to the document itself. As I mentioned, the document itself was loosely based on what was done in Mississippi. We started off focusing on West Tennessee. It's now encompasses the whole of the state. And we envisaged looking at 4 or 5 different phases, starting with getting a committee developed and a draft document, then going in and looking at water quality trends across the state, and then looking at how we get stakeholders involved. What kind of information education things do we need to do to get the word out? These are some of the practices that we would like people to use to help reduce the loss of nutrients from agricultural lands. And the third phase there, phase 3, communicate the results to the public, and then in a periodic time evaluate and revise the plan. I will mention this meeting we held in Jackson at the end of December, at the end of 2011. It was held with a number of agricultural professionals from the USDA, Department of Ag, the Farm Bureau, as well as ourselves at the University of Tennessee, but also, very importantly, a lot of people that are actually directly involved in agriculture. Some of the big row croppers from West Tennessee as well as Middle Tennessee were invited. And they gave some very good feedback on how we should get people more involved. And we got some revisions suggested to our plan, which we enacted. And we came up with our plan, which we mentioned we released in April of the following year. Our plan is really much focused on, well, what do we know that works in terms of agricultural practices and soil management that will help reduce loss of nutrients. Remember, if we're going to be buying expensive fertilizer nutrients and we're losing them, that's obviously not a very good for the bottom line for your economics. But it's also not very good for the environment. So some of the key points from our strategy is basically follow the University of Tennessee soil test fertility and other recommendations. We are tasked at the University of Tennessee to generate science-based recommendations on fertilizer use. So rather than use recommendations from people that haven't got the research background or are getting their research recommendations from out of state, use the University of Tennessee. We also want to encourage people with the use of no-till. We'll talk a little bit about no-till or no-till adoption, as well as some other emerging practices. Encourage the use of winter cover crops, the adoption of different precision agricultural technologies. And in order to show we are making progress in this, we need to document how the adoption rates of these particular practices are changing. For those of you who don't know, and I'm sure most of you do know, this is a typical kind of way that we do no-till. If we look at start off in the top left-hand corner, we have a cover crop. This is a picture of a winter wheat cover crop, which we, in the springtime, we terminate, usually with a herbicide, to kill it off, and then we will directly plant using a no-till drill into the soil with minimal soil disturbance. In the past, we would have completely inverted that soil, creating all sorts of erosion, and then we directly seed, put the seed into those slits, and while maintaining the previous crop's residue on the surface. The big thing is minimum soil disturbance while protecting the soil surface at all times. Tennessee is really at the forefront of the adoption of no-till. One of the reasons being the very high rates of erosion, and we'll give you an example of that in the next slide. But no-till adoption we've been working at in the University of Tennessee since the late 70s, early 80s. Really started to take off in the 1990s with corn systems. Big thing took off in the middle of the 90s when we had much better herbicide packages. There was a number of extension work that was done, as well as policies that came out by USDA to encourage the use of some of these practices on our more erodible soils. Mid-90s, we saw the emergence of different resistant traits in our main crops, in corn, soybeans, and cotton. And you'll see this graph on the bottom This is where we really started to see an uptick in the adoption with the introduction of Roundup Ready resistance in the corn, soybeans, and cotton. I've got this report from 2018 looking at tillage systems in Tennessee. And you can see here we're reporting that soybeans had over 85% adoption of no-till across the state. Cotton had 80%, and corn had 75, almost 76%. So we are amongst the highest rates of adoption, I would say, in the country, if not the world. So why was no-till adopted so well? It's because of our very, very erosive soils, especially in the western part of our state, our loess, the soils derived from our loess soil, these wind-blown materials. I like to use the example here of the revised universal soil loss equation. I don't want this to become a kind of soil science lecture where we talk about the factors involved in this. It's good to know the R factor here is the rainfall, the intensity and the duration of the rainfall. The L and the S are the slope factors. How long is that slope? What is the angle of the slope? The K factor is how erosive is the soil. And then the C is the cover. Is that soil covered? Is it covered with residue from the previous season? Do we have a living plant growing anything, or is it bare fallow? And P is the type of practices that we're doing. Use the example of a soil from Gibson County. This is from West Tennessee, where our research station at Milan is located. If you look at corn in a conventionally plowed system in Gibson County on this particular soil, a Granada soil on 2 to 6% slope, if we go from plowed to no-till, we dramatically reduce the amount of erosion from 64 tons to the acre per year to less than 2 tons, 1.4 tons. Can we do a better job? Yes, we learned that if we put a cover crop behind it, we can reduce those erosion rates to less than 1 ton a year per acre. Compare that with 64 tons, now we're at less than 1 ton. Corn is a very good at reducing erosion rates because of the heavy amount of residue that's left on the surface. Soybeans and cotton, not so good in terms of the residue that's left behind, but you can see in the soy system, plowed 95 ton soil loss per acre per year, cotton 100 tons soil loss per acre per year. Moving to no-till, we get down to 14 tons per acre per year with soybeans. With a cover crop, less than 4 tons. With cotton, the examples goes from 100 tons to 19 tons to less than 5 tons. So this shows if we're wanting to reduce, if we can reduce our soil erosion, we're obviously going to be reducing the amount of nutrients we're losing. So we're very much encouraging the continual adoption of the increased adoption of no-till. Can we do better? Yes, we believe that example with the revised universal soil loss equation shows that if we add cover crops, and cover crops have very many benefits, and cover crops typically are crops that we plant after the main crop. Typically in the past we grew a wheat, sometimes we'll grow a legume, and these days we're growing a lot more mixed species cover crops. But they, in addition to reduced erosion, especially in the winter months, we can also suppress weeds and reduce the needs for so many herbicide applications. And we do know that we can increase some of the infiltration rates. Obviously, if we increase our infiltration rates, we have less runoff. Less runoff is less erosion, less nutrient loss. We know that also the use of cover crops, we can see some increased yields. We've found this, we have a study which we started in 2013 at Milan, where we're looking at cover crops and influence on the yields. This is a soy corn rotation. 2016 was a dry year, and we did see a significant increase in yields there. Other years, we didn't see any significant difference in yields, basically because we had fairly adequate rainfall. Other issues to consider when we're looking at cover crops is that when we terminate these cover crops, they typically decompose very quickly. Usually about half of it decomposes within the first 4 weeks. So to get the maximum benefit of the cover crops and protecting the soil surface before the crop has emerged, we really need to time our termination very carefully. We also know that with some cover crops, for example, cereal rye, we can impact the performance of the corn if we're growing corn afterwards. And so one of the things that we're looking at there is how do we reduce the potential for a negative impact from some cover crops such as cereal rye. Typically, we're now recommending that we, rather than spread out our applications of nitrogen fertilizers, that we want to put all that nitrogen fertilizer out, when we plant the crop, and that helps break down the cereal rye crop. Other things that we're learning is that with these cover crops, we do have what the entomologists like to call a green bridge. So we go from one crop to the next, and insects can carry over. And so we're very much recommending the use of insecticide seed treatments if we're doing cover crops to reduce the potential for seedling damage to early emerging insects. Now I'm going to shift gears and talk a little bit about the influence of cover crops on and tillage on water infiltration. Water infiltration is very, very important in nutrient loss. If we've got more water infiltration, we've got less runoff, we've got less potential for erosion and or just nutrients being carried in that runoff. This is a study that was completed at the end of 2019. This was based on a long-term continuous cotton experiment started in the early 80s in Jackson, Tennessee. And what we're looking at here is NT no-till compared with conventional till. And you can see the water infiltration rate. So overall, the infiltration in the no-till system was almost 3 inches per hour, whereas with the conventional till, it was about 1 inch per hour. So if you think about having a large rainfall event in the no-till systems, we're going to be capturing much more of that water in the soil profile. You'll see there's also differences between the different cover crops. So in the no-till system, with no cover, we've got 2.5 inches of infiltration. If we've got a cover crop, a vetch or a wheat cover crop, we've got almost 5 inches or over 5 inches with the two different cover crops. Compare that with the infiltration rates under the different under the conventional tillage system. So take-home message here is tillage, reducing your tillage, and including a cover crop increases the infiltration rates. This is also manifests itself in the amount of water availability during the dry periods. This is information from the same study. And you can see there was much less water available in the conventional tilled compared to the no-till, and the more water in the cover crop treatments compared with the no cover crop treatments. This is a very, very busy slide where we looked at the yield of the cotton in this whole study period from the mid 80s to present time. What I want you to take home from this is not necessarily understand what's going on, but you can see the cover crop treatments here are in colors, the red, the yellow, and the green. And you'll see in these lower years when we had low rainfall, the cover crop treatments are always outperforming those with no cover crops. So this shows you the long-term trends of using cover crops in terms of yields, maintaining a yield stability. Some results from some other work. This is work that was done by my colleague, Dr. Sean Hawkins, looking at modeling water flow in the South Fork of the Obion River. This is just an example just to show that we calibrated the model to our observed readings were very similar to the actual readings. And what he did was looked at converting some of the land to cover crops. And he noticed that if you used a winter wheat cover crop, you could reduce the amount of nitrogen that was being lost by up to 59% just by adding cover crops. If we added cover crops, the phosphorus reduction was a little bit less, but still significant at 12%. Let's talk now a little bit about some of the precision agricultural technologies. Precision agriculture is not one practice, it's a whole suite of different practices. Think of it as a toolbox where we're trying different things. And these are some of the things we talk about when we talk about precision ag, using different guidance systems and different ways of applying different rates of fertilizers and lime and at different times of the year. I'd like to recognize my colleague, Dr. Mike Bushimo, for some of these slides. And these are just an example here of variable rate applications. We've got, 2 fields here. And we're looking at applying diammonium phosphate here. One at a blanket rate. If we applied 60 pounds to the acre uniformly across this whole thing, we'd be looking at applying over $5,000 worth of fertilizer. I'm sorry, 5,000 pounds of fertilizer at a cost of about $1,100. Variable rate, and you can see the patterns of the variable rates is based on soil sampling and grid sampling. You can see we're no longer applying the blanket recommendation of 5,000. We reduce the rate by 2,200 pounds. We reduce the amount of money we spend to $600 to the acre, with a savings of almost $500 to the acre. So not only are some of these technologies good for the environment, good for reducing our nutrient loss, but also great for the economics and saving money. One of the things that we do need to still consider in the future is trying to collect data to support our efforts in reaching the goals of our nutrient reduction strategy. We are working actively with the Department of Ag and others to conduct surveys to find out how many people are actually using our UT recommendations, and are we seeing an increase in the people following our recommendations. We're also trying to figure out how many acres of more cover crops do we have now than we did have a few years ago. Currently, we believe about our adoption rates about 10 to 15%, so we've got plenty of room to further increase adoption rates. And what kind of precision ag technologies are people changing? And then hopefully the idea, if we can map these trends in different practices, we will see changes in the amount of nutrients being lost from the field, and then ultimately we'll see less of a problem going into the Gulf of Mexico. Recently heard that back in the middle of last December, EPA was sued again by a group, a consortium of different people. You can see this is from the actual act from the Sierra Club, as well as various other things. And once again, the EPA was being sued by these environmental groups for not developing numeric water quality standards for nitrogen and phosphorus in the Ohio River. And they're asking that the EPA force people to develop a total maximum daily load, which is basically a nutrient load budget for the Ohio River, which is this purple thing here, a very large area here. So this obviously ongoing lawsuit, it was filed during the last few weeks of the last administration. So we'll be on the lookout to see what the new administration is going to do and how they're going to act on it. I know from ourselves at the University of Tennessee, as well as talking to colleagues at the Department of Ag, as well as Department of Environment and Conservation, we believe we are on the right track with our nutrient loss reduction strategy, rather than trying to set these numeric standards, which really don't help us in implementing change. And with that, I'd like to thank you for your time, and thank you.